Hello, everybody. So I figured I'd give you some examples that you could kind of just watch me do if you'd like. Sometimes that helps some people. If you'd rather kind of hit pause, try and do it yourself, try and think it through yourself, then right away, then watch what I did to see if you did the same thing or not. That's fine too. Um, Make sure that you don't watch the videos for the assignment sheets without having done them first. If you just want to watch this video straight through and watch me do some examples, that's totally fine. But don't do that for the assignment sheet problems. That's just a waste of your time seeing me do those problems without you trying them first. It's not good use of your time. But let's watch these. So let's start with a problem like this. And for a problem like this, I could ask you multiple questions. I could say, hey, does this converge or diverge? But for a problem like this, I could also stipulate if it does converge, what does it converge to? So I could ask you that. So the first thing we have to do, some of you might see it right away, but some of you won't. So we could start writing out the first terms. If we put in 3, okay, we put in 1. So think about n equals 1, n equals 2. We could kind of think about what are these first terms. So the first term is going to be 3 times 2/5. I think that's 6/5. The next term is 3 times 4/25. 3 times 8 over 5 to the third. 3 times 16. Okay, I think I'm going to stop there. That's what the sequence equals. And some of you need to write that out to see it. Some of you saw this already, that there's just a common r of 2/5. It's multiplying every time by 2/5. And you can kind of see that if you think about this as 3 times, right? That's another way of looking at it. So therefore, we have a geometric series, and r is less than 1, like the r is 2/5, and it's less than 1. So therefore, we have converge. Whoops. We have it converging. And we have it converging. And if we wanted to, we could say, what does it converge to? We could definitely answer that question. We could answer that question by just figuring out the thing that we used before. This beautiful little formula only works when r is less than 1, or I should say the absolute value of r is less than 1. We can say, okay, our first term is 6/5. 1 minus 2/5. Oh, is that 2? That's awesome. That's just 2. Okay. Now, for other problems, I can do that. I can't say to you, hey, why don't you, figure out the exact sum. Some problems I can just give you another kind of question that says converge or diverge. So this one here, let's figure out, does it converge or diverge? Well, some of us see it right away. Some of us don't. If you wanted to kind of start doing what I did earlier and kind of writing out the terms, it's going to get nonsensical really fast. I'm already starting to be like, what the heck am I doing, right? This makes no sense. So let's not do that. That's not a really good use of our time. Instead, let's go back and start thinking about, can we rewrite this algebraically? And if we rewrite this algebraically, hopefully we see it. Oh, 2/3 is less than 1. So by the p-test, the series diverges. Now, one of the things that you have to recognize is that 2/3, is less than 1. You have to recognize that pattern. That's something you want to get used to seeing. Someone comes along and gives you this now. You may say to yourself, whoa, I can't do the p-test. You're right, you can't do the p-test. You have to recognize immediately the p-test is not allowed because you don't have a simple p on the bottom, you have this +1. Now we all know that +1 in the long run is meaningless, right? We know that, but we can't use it. So the one thing we could do is say, well, what's going to happen? well, I could start thinking about this, what's going to happen 1 over, you know, some really, it's going to be a number that gets kind of large, it's going to get big. But I could start thinking about what's this term here. Well, I could say that as n goes to infinity, this new series that I have, this series that I just created, and the series that I just approved moments ago, moments ago, that's the same one I just did. That's the number 2. Let's think about this. What is this going to happen? What is this ratio going to get closer and closer to as n goes to infinity? Well, I think, I'm not going to belabor the point too long. They both, in the denominator and numerator, have a degree of 2/3. So I think that's going to be 1. And this doesn't equal 0, right? So the limit of the two terms, of the term divided by the other term, the term of one sequence, the term of one sequence divided by the term of the second sequence, the limit of that as n approaches infinity is some non-zero constant. Since it's some non-zero constant, what does that mean? It means that the two sequences will converge or diverge together. Well, we know by this up here, we said, hey, we just said moments ago, it diverges, right? So therefore, they're going to diverge together. This is using the comparison test. It's really important that when you're using the test, you talk about what test you're using. I'm sorry, I said comparison test, I lied. The limit comparison test. That's not the comparison test. So when you're using these tests, it's important that if you're using the comparison test or the limit comparison test, that you clearly talk about which of the two that you're using, and you clearly show the kind of series that you're comparing it to, and whether that series converges or diverges. You can start anywhere. Okay, we'll just do this. How about 2 to the n? Make that a we'll make that an 11 for fun, and we'll make that plus 1. Okay. Well, I mean, it feels like the denominator is getting big really, really fast. It feels like it's going to converge. That's my instinct. We can come over here and we can say, well, let me compare it to, what about this sequence right here? If I look at this, that's a geometric series, right? And this guy here is always going to converge, because it's a geometric series with r equal to 1/2, which is less than 1. If you don't see that, folks, you can just rewrite it like that. Okay, so we have a nice, beautiful sequence that we know converges. And now we can think about this guy. Well, this denominator on the left is bigger than the denominator on the right. If this denominator on the left is bigger, that means the overall fraction is going to be smaller. And this is true for all n, right? This is all true for all n, that this is going to be true, that this guy on the left is smaller than this guy on the right. This guy here converges. Therefore, this guy also converges by the comparison test. So there's four problems, sorry, that I just gave you that can kind of show some of the stuff we just went over. Um, I highly recommend now you spend some time on the assignment sheet and see how you do. And then you can look over the answers after you've had a chance to kind of work through some of those problems. Talk to you soon.